So there's our summary of all our interconversions again. With that, we will kind of move forward. Actually, I think the very next reaction, yeah. So what we talked about was how these things stacked. That once you started at the top, you could always work your way down, but it was very hard to work your way up. Okay? Are there any weird exceptions on this that you happen to notice that you're like, but that's working its way up? So for instance, we definitely have the outside one works its way up. But that one works because we have thionyl chloride, and that's just super, super reactive. Thionyl chloride is like all the way above it. The bottom seems a bit odd, right? Starting with the carboxylate, making it to the carboxylic acid. Okay. Well, how does that one work? You add a really strong acid. That reverses that. Okay, so we can reverse that by adding a really strong thing. So both of those kind of make sense. What's happening with the one right above it? How about the amide to the carboxylic acid? So both the acid one and the thionyl chloride are both putting in something massively reactive to force that reaction to occur. What are we adding in the blue step? Adding water. Oh, that's right, because water is super reactive.
Causing the lead group to leave.
Oh, okay, so...
Replaced by the OH.
But that kind of thing is happening all the way through this. Why is that reaction allowed to happen? That's going up in energy, okay, or up in kind of activity on our scale. Okay? In the cases where we went up, we had to add something super reactive. In this case, we're adding water. That's not super reactive, and yet water is somehow able to convert the amide, a lower rung on our ladder, to a higher rung. That's kind of weird. Okay? And so most people would look at that and call that an exception. Okay? It's not an exception. We have to evaluate the mechanism. What were you going to say, Farzan?
Is it because nitrogen is a better base than oxygen?
The nitrogen is a better base. Okay, but it's not acting as a base here. Okay, so it's going to be addressing the mechanistic steps to see what's happening within this. And that does kind of come up in the synthesis. Okay, so if we go through and look at our reaction, okay, for the amide, we can convert the amide to the carboxylic acid in pretty darn high yield. That's a 96% yield. Okay, so this is really saying this is an easy step to do, and yet the amide is lower in energy than the carboxylic acid. So why are we able to make this jump? Let's look at the mechanism. This could run under basic or acidic conditions. It doesn't really matter, but it's shown here under basic. Okay. So in the first step of our reaction, what happens? The hydroxide attacks our carbonyl carbon, breaks the pi bond. Okay? So another way, we neutralize the negative species first. Go away. Not you, by the way. You should stay. And of course, the image that the textbook decided to use with these massive ring structures, but ultimately it doesn't matter. And we'd have that negative oxygen up there, right? What happens now?
The electrons from the oxygen come back down.
Okay. Which thing would be more stable, O minus or N minus? O minus. So if it kicks out O minus, what happens? We go backwards. And nothing happens. 96% yield. Okay, what does that mean? Nitrogen has to be kicked out. Okay? We could run the assumption, oh, well, maybe we have to protonate it so it becomes a better leaving group, so it wouldn't be charged. Can we protonate it? Why not?
Basic conditions.
Basic conditions, I can't put a hydrogen on there. Okay? So I'm going to go through and show that as the product. I may not be happy about it, but according to our results, this needs to happen. Right? Make sense so far? Okay. That nitrogen is a better nucleophile than the oxygen because it's not as electronegative, so it could theoretically attack, and our equilibrium would very heavily favor our reactants. Okay? That becomes a bit problematic, because isn't that what I want for my product? Yeah, so what's going on here? What is the functional group now in purple? Carboxylic acid. What is the functional group that we had drawn in red? It's an amide, which could act as a nucleophile. It could also act as a base. Amides tend to be very basic. Remember, if we just had nitrogen, we said that's a nucleophile or a base. It wasn't an acid. It acted primarily as a base. That was a neutral nitrogen. This is a negative nitrogen, suggesting this is a strong base. What's going to happen when we are in the presence of an acid? It's going to deprotonate the acid to produce a product. So let's take a look at what that product would be. Yeah? Okay, where we now have that hydrogen attached to our nitrogen, and we have the negative oxygen. Which way should that equilibrium favor?
That's right.
Is it even in equilibrium? No. Remember, the amine acts as a base, not as an acid. I'm now at an amine. Okay? The amine acts as a base. To reverse that reaction, the amine had better act as an acid. It doesn't act as an acid. That reaction is not an equilibrium reaction. That is unidirectional. How does that facilitate and get us to a higher yield of our product? Because as we move through, we have a pretty even equilibrium for our first step. The next step of the reaction heavily disfavors our product. Okay? So if we looked just based off of those first two steps, we would expect an incredibly low yield for our final product. Okay? Probably less than 1%. Okay? So what happens then? Why am I allowed to now get so much product, a 96% yield? That very tiny 1% of product I make then reacts with itself or with the other reagents to do what? To form a new product. That step is completely irreversible. So that 1% of product now disappears. What does the equilibrium say? Make more product. I make another 1% that immediately goes irreversible. Eventually what happens, all of that tiny 1% equilibrium of product gets converted across to our final product. And because that final product can't reverse, I'm now there. Right? But is what I've got shown here the correct final product? No. What's wrong with it? It's charged. How do I fix that charge? Protonate it. How would I protonate it? Add H+. I add a strong acid. Cool, nice and straightforward. We put that hydrogen on, and we could then say we're done. We've got the carboxylic acid. So the focus here was converting the amide over to the carboxylic acid. Secondary focus, notice the other product is shown in parentheses. Why did they put that in parentheses? What did we say the amine was? A base. Okay? I've now formed a base that I just added acid to. What happens to the amine? It also gets protonated. So yes, I form the carboxylic acid as a product, but I don't form the neutral amine. What do I form? I form the positively charged amine. Now I can ditch those parentheses because now I have my correct product. Okay? So we have to remember our amine chemistry. It is primarily a base. Okay? Be careful with it when you move through. Okay? It is that secondary characteristic that drives this reaction. If we didn't get that acid-base step at that last one, this reaction doesn't work, and we don't convert between the amide and the carboxylic acid. Go ahead.
Would the carboxylic acid be the main product be more stable because of the resonance stabilization from that product?
Say that again?
There's charge in that in the top one, because there's
Yes.
a positive charge. Why
On
would
the
that
neutral.
not be a more stable negative charge than that positive charge is because of the resonance?
If we looked at just those structures, you're probably right. Don't forget to include the strong acid. The strong acid is what's going to drive that. You're killing that positive. That H+, so the the conjugate base of our H+ is more stable than the conjugate base of our carboxylate. That's what's going to drive it. But that's a good point to take a look at that. Questions about that? Okay. So that's kind of a neat one. And I believe, Wyatt, you actually asked about this in office hours. This is a way that we could form amines. We don't typically use this as a synthetic tool for making amine structures. Remember, like the varying substitution patterns on our amines, we can really only directly synthesize the quaternary amine. Okay. This would be a secondary amine. We wouldn't use this as a synthetic method because we got it from the amide. Well, how did we get the amide? From the amine and the carboxylic acid. So you already started with that level of amine. Using this to make the amine is a bit silly, right? Not cost effective. Right? It would be like using petroleum to make hydrogen to burn in hydrogen fuel cars. Just burn the petroleum in the fuel car. You remove a step. Okay? So, in our free energy diagram, if we look at those first two steps, we are higher in energy with that carboxylic acid, which would suggest the equilibrium does not favor our products. We're endothermic all the way through. What happens is the now hidden step where we do that acid-base step. The resonance stabilization within your conjugate base of the carboxylate is really what drives that. Okay? It is that irreversible step that forces this reaction to occur. We then follow that up with our second step of adding the acid. Okay? Kind of makes sense? So just another way to look at it, because we've looked at some energy diagrams before. Okay? So let's look at an actual way to synthesize amines. So the synthesis back here, kind of a bit silly to generate your amines, because you're starting with the amide. Okay? And the amide we probably got from amines. So it seems a bit odd to use that synthesis to make amines. Right? We can still take advantage of that same chemistry to make new primary amines. In the previous case, we end with the same amine that we started with. That's not very useful. The Gabriel synthesis takes advantage of that exact same concept, or that exact same reactivity that we get within that previous system, or the interconversion between the amine and the carboxylic acid, to make new amines. Okay? So we still have our hydroxide present, just as before. Okay? In the previous mechanism, what did the hydroxide do? It attacked our carbonyl. Okay? And it did not attack what? It did not attack a hydrogen on our nitrogen, which in the previous case we didn't have a hydrogen there, so that could be an explanation for why it didn't do that. Okay. Why would it attack that nitrogen? Sorry, that hydrogen.
That would be the most reactive species.
Why is it reactive?
It's acidic because the nitrogen's electronegative when the atoms back away from it.
But that would mean nitrogen would act as an acid, and nitrogens don't act as acids, so I don't accept that explanation.
Resonance.
There's likely to be a resonance argument here. Okay, that resonance stabilization of that charge is really what's going to help us out. That resonance was already there, okay? And there's also kind of now a double effect of an inductive withdrawing because there's two oxygens there. So the nitrogen can't do resonance to both carbonyls, but one of those carbonyls can act as an inductive withdrawer to make that nitrogen even more acidic. Okay? So there's lots of things contributing to this nitrogen being more acidic than a standard amine. Okay? Resonance, induction, and very arguably a hybridization effect too. Does everybody see the hybridization effect? If we do resonance, what does our structure look like? Yeah, but if I'm talking about a hybridization effect, we're talking about the stability of that nitrogen. What is different about the hybridization? This one would be sp3, this one is sp2. As we become less p character, more s character, our atom becomes more electronegative. Right? So there's lots of contributing factors to make that hydrogen actually pretty acidic under these circumstances. A standard amide, not quite as much. Okay? We really need that double carbonyl effect for us to set this up. Okay? The important part is we remove that hydrogen. And we now have a negative nitrogen. So what can happen now? Oh, shnikes. What can happen now is buried underneath that white box, and if I click the button to reveal whatever that white box is, I'm going to lose all my drawings. So we're going to say it says CH3CH2Br. It does? Cool. What does that structure bring in? I don't quite accept CH2, CH3. That's not super relevant. What I want to hear is the reactivity. What is the reactivity of that structure? It's an electrophile. It's electrophilic where? At the CH2, because the bromine is a good leaving group, right? So what can happen is our negative can attack the CH2, kicking out the bromine. What kind of reaction do we just complete? Rhymes with poo. It's one of my best rhymes. It's an SN2 reaction. You're like, oh, he's tired again. Yeah, it's an SN2 reaction. Backside attack, strong nucleophile. Right? And we would have our product. Right? We're still under basic conditions. Do we have an acidic hydrogen anymore? No, so what can happen? Now the hydroxide can come in and attack, forming our tetrahedral intermediate. And for those of you wondering why the textbook didn't show all this, it's because it is long and tedious, and I'm probably going to stop showing it in a little bit too. Now what happens?
That launches the nitrogen.
Our electrons can come back down, kick out the nitrogen. Oh, monkey. What functional group do we have on top? Carboxylic acid on the bottom. And amide. How do carboxylic acids react? As acids. And how do amides react? As bases. We can get the intramolecular acid-base reaction. Any complaints with that one? It's intramolecular acid-base. What did I say about intramolecular acid-base? Doesn't happen.
Would it react with something else, another molecule?
Arguably it does happen. Why is it allowed to happen this time around?
How close they are?
1, 2, 3, 4, 5, 6-membered ring in your transition state. Good counting. Okay. It is that 6-membered effective transition state that allows the intramolecular reaction to likely happen. That's also probably one of the reasons why this reaction is so good. The result is we've now done the completely irreversible, because technically all of these other steps were reversible. Not that substitution. Done our completely irreversible to form the carboxylate. CH2, CH3 with our nitrogen. Hydrogen. Right, but we're still in a basic solution, so what can happen? You do it all over again. We attack, break the pi bond, reform the pi bond, kick out the leaving group, have that basic nitrogen deprotonate the hydrogen. Right? We would then have the primary amine. We could arguably add acid into this. We don't need to, because the goal of the Gabriel isn't to make the carboxylic acid. The goal of the Gabriel synthesis is to make the primary amine. It's already neutral. The phthalimide structure is now negatively charged. The negatively charged structure is very likely to be soluble in water. The primary amine won't be. I can do a simple extraction, and I can remove all of the bulk of that structure and leave me with the primary amine in my organic solution. Hey, look at that, I was right. Okay. And I now have the primary amine. Okay. 57% yield. You know, I said, well, that isn't very good, but if we looked back at our yields for the primary amines in the standard substitution reaction back in chapter 10, our yield was pretty piss poor, and it generated the secondary, tertiary, and quaternary amines that have virtually identical solubilities to the primary amine, which means not only do we get a piss poor yield, but we have no way of purifying it. Here, we may get a lower yield, but it's really easily purified. Okay? So we get kind of two steps that make the Gabriel synthesis more advantageous. Make sense? Yes?
So, oxygen, hydroxide, not being a stupidly strong base or nucleophile.
It's not a stupid strong, yes, but it is
So-
still strong.
Yeah, and we have nitrogen, which has a lone pair, which can have resonance with
Mhm.
carbon, which makes the carbon less electronegative and less electrophilic.
Is everybody repairing with that?
Yeah.
He's saying that carbon now is not an electrophile.
Well, the other one would be.
What about the other one?
You have two.
The other one is now very active as the electrophile.
On the other side.
So after the first step, why the second one?
So, and then, which would be the next good point to go through and ask, and we would say that, yeah, that doesn't make sense. There is a stabilization there, right, which would go, let's see, did I actually draw it? Do we have a nice picture of it? Come on. That's what the energy diagram is showing here. Okay? That oxygen could attack that electrophilic carbon. That's a poor electrophilic carbon, which is why our intermediate's higher in energy. Which is why when the oxygen gets kicked out, or sorry, the nitrogen gets kicked out, it's higher in energy. All of that says that that reaction doesn't work. That electrophile isn't electrophilic enough. Right? So we end up with a horrible yield. But then what happens? It's the acid-base step that drives that reaction. Everything beforehand, yes, horrible, sucks, wouldn't do it. But it does it enough that the equilibrium gets shifted because that next step allows for it. Okay? Which is kind of a weird statement to make, because what we've done a lot in the past is just say, just go through and do it, and if it doesn't make sense, go backwards. Here we're going through and saying, well, we do it, well, that doesn't make sense to do, I'm going to go backwards. You have to evaluate that next step and say, does that next step help? Nothing is wrong mechanistically here. Okay? And that's the other thing that we have to consider. In a lot of the previous cases where we've encountered, and I said, well, you can't do that, it's because you've done a mechanistic failure. Okay? There's nothing mechanistically wrong here. The energy difference between those two isn't enough to make things too far off skew, that this reaction does occur at very low yields. It's that last acid-base step that kicks that into overdrive and allows us to actually make the final product. Kind of make sense?
Thank you.
Okay. So we really have to keep that in mind. And this is one of the frustrating things. Back when we had the oxygen nucleophile and just did nucleophilic additions, and I said we had to deal with equilibriums, and we just had to deal with it, we just had to do it and see what happens. A lot of these mechanisms are you do it, and you be like, I don't really like that. Let's just see what happens if I do one more. Oh, that one more is really favorable. Okay, that's probably what's going to happen. Right? And again, ultimately, this isn't someone sitting down at the table just drawing this out. Because if someone drew this out, they probably would have drawn that and said, that's crap, I'm not doing that. Right? What happened is they drew it out, said, nope, that shouldn't happen, now I can do something else. Okay? I'll do some other chemistry where maybe I want the phthalimide, okay, attached. Maybe I want some big goofy structure after that substitution. Okay? Maybe they went through and said this was my target molecule for whatever reason. Okay? And they didn't get it. Okay? And it's that didn't get that now made them go back and say, whoa, why did I not get it? Okay? A lot of the reactions that were obvious weren't named. This is one that you're challenging. You're saying that shouldn't happen. And yet what happened? It did. So what happened with the reaction? It got a name. Okay? So a lot of the named reactions have something in them that make us go, I don't really like that. Okay? At least the named reactions that are worth anything. Sorry, Markovnikov. Advantageous. Okay. So why do we need it? This goes all the way back to chapter 10. We've got a primary amine. Okay. If we just used ammonia in the alkyl halide, we get pretty piss poor systems. Okay. And if we go through and look, notice it's a 57% yield. It's exactly the same. Come on, why would I not do that? The secondary and the tertiary will now compete, or not compete, but make it difficult to isolate the primary amine. Okay? If I can't even isolate the 57%, it's not a 57%, it's a 0%. Okay? How do we know it's 57? Someone probably went through and stuck this through an instrument that separates things based on atomic mass so that we could analyze the pieces. What instrument did that? Mass spec analyzes masses. Okay? To separate them by their mass, we typically have to do something like a GC, okay? Or gas chromatography, which was mentioned in lab, but we didn't use it. Okay? So by linking those two instruments together, we could determine the percents of these, but we would be virtually impossible to actually isolate any one of those amines. The Gabriel synthesis forms the primary amine. The byproducts of it are now waste, and I don't have to worry about them getting in the way. Those disappear very easily because those intermolecular forces are significantly different. Kind of makes sense? Okay. So it's kind of neat. At least I kind of find it neat. Okay. Alpha halogenation, or the haloform. Right? This came from our Unit 1, and I believe I might have also dumped it in the Unit 2 exam. Right? What happens under basic catalysis? So we ran this reaction, but not with an acid, with a base. What is the result? Predict your product. Okay. So, couple pathways come to us. Number one, the hydroxide is active as a reactive species, as a nucleophile, because it is negatively charged. It is also active as a base. Okay? So we could go through and have it act as a nucleophile. There's really only one electrophilic site. That would be that carbonyl. That looks a little sloppy, but it's there. Right? Okay. So, drawing it out, not a bad idea, but now you got to evaluate, is there something that that structure could do? Okay, we're kind of dead in the water. We have a negative oxygen, so that could potentially act as a nucleophile. Okay? But would I form an OBr bond? No. Okay? So it doesn't really address the other reagent that's present. Okay? If I further evaluate stability, negative oxygen versus what I started with, negative oxygen. At best, I'm in an equilibrium, a weak equilibrium that oscillates back and forth between these. Nothing really takes me anywhere. Okay? That functional group should look really similar or really familiar, particularly if I added a hydrogen to it. Because what have I done? I made the hydrate. And what we should remember from the nucleophilic addition chapter is that hydrates are not stable and will revert back to their carbonyl state. Okay? So the hydrates are really just kind of a temporary intermediate. If there's chemistry available in solution, they'll continue to react. But there isn't really anything for this to react. Okay? So I like that idea. It unfortunately went nowhere. Okay? So now we've got to evaluate the strength of our base. Right? Well, if it's going to act as a base, it needs to react with an acidic hydrogen. Where are there acidic hydrogens? At the alpha positions of the carbonyl. Why are the alpha positions acidic? Because there's a resonance stabilization with that carbonyl. And it is that resonance stabilization through what functional group? The enolate that gets us our active chemistry in this case. That negative can come back down. The electrons go out onto our carbon in our resonance structure, okay, showing us our worst, or our best worst resonance structure, which sets us up with a nucleophilic carbon. With a nucleophilic carbon, I can now have the electrophilic bromine actually have a sensical bond. And we'd end up with our final product with the bromine attached. Okay. This didn't make it into the video, but I said there were 4 acceptable answers, or 4 answers that I would have accepted. This would be one of them. It is also wrong. Okay. Why is this answer wrong? Okay. There are still alpha hydrogens. Okay. What is special about that product structure in comparison to our starting carbonyl? It is more active as an acid because bromine is electronegative, which means it pulls electrons further from the carbon via induction. And we have an inductive effect making that hydrogen more acidic, so it does it again, forming product number 2. Also wrong, because I have another alpha hydrogen. That structure is now more acidic than the previous one because more induction. Okay? So we run through that cycle again. And we'd end up with our third wrong product, because we have yet another acidic hydrogen. That structure is even more acidic than all the others because more induction again. Okay. This is one of the reasons why when we talked about the alpha halogenations the first time around, we said base catalysis was generally a bad idea. Okay. We wanted to run under acidic conditions because that would do a single substitution. Base catalysis does multi-substitutions. Okay. Well, that was all review, so that was kind of boring. Okay. We did also mention this reaction, where we take NaOH, which is a strong base, in the presence of Br2, same thing would happen. We would do our alpha halogenations, okay, and we would expect that any position with a hydrogen or alpha hydrogen would be deprotonated and replaced with bromines. So our final product should look something like this. And for those of you being like, well, Mike, you already drew the product. Did I? And yet something else is happening here. What are you suggesting, Wyatt?
The electrophile of the carbon.
What did we say the hydroxide could act as? A base, and it could act as a nucleophile. It can only do something useful as a nucleophile if there's some other chemistry available to it. Okay? And this one, I would argue, is not easy to go through and see, but if it goes through and attacks, yes, we form our tetrahedral intermediate, which is vaguely like an acetal. And you might say, well, I don't see anything useful here for us. Okay? However, if that negative comes back out, it can kick out that structure as a leaving group. And you might say, well, isn't that a bad leaving group? And why would you say that? Because it's a negative carbon. And carbons are notoriously not good leaving groups. So why is that okay as a leaving group? It still has to leave first. I need an explanation for it leaving. Yes, you're right. Once it forms, it could go through and do this. Okay? But if it can't form because it's not a leaving group, that's not going to happen.
The induction effect from the bromines, those are so negative.
Those bromines are so electron withdrawing that that allows that carbon to exist for a long enough time that it can remove the acidic hydrogen. Once it's removed that acidic hydrogen, okay. Actually, I missed 2 steps. Missed 1 step. But I'm not going to show the full product. We would end up with the HCBr3 and the conjugate base, which we would then add H+ to then protonate and get us to the carboxylic acid. So we could convert the functional group we started with to a carboxylic acid through this process. What functional group did we start with? We started with a ketone. I know why you want to say an aldehyde, because you saw those hydrogens out there. Okay, be careful, there is a carbon there. Okay, so what did I start with over here, though? A ketone, and yet where did I stop that reaction? What functional group did I end that one with? A ketone. Why all of a sudden a switch? When I move to the box one, I start with a ketone and I end with a carboxylic acid, but the left one, I start with a ketone and I end with a ketone.
Because there's another bond with the carbon that would disallow leaving.
Yes. Okay. The leaving group ability really comes down to those 3 halogens. 2 halogens is not enough to stabilize that negative carbon. We need the 3 halogens to help withdraw the electron density enough to act as a leaving group. Okay? That's our big piece. We have to have those 3 pieces. Okay? Which means I need 3 hydrogens on an individual carbon, which means I have what functional group? This is where you had it, Sam. We have a methyl ketone. So if I have a methyl ketone structure, I can do this conversion across to the carboxylic acid. Okay? Which is kind of neat. At least I find that chemistry kind of neat. Okay? And more interesting, it is really, 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 really fast. Okay? That reaction happens within seconds, speed-wise. Okay? Any reaction that happens very, very fast and with very particular functional groups can then get classified under a special category. That category is known as the classification tests, okay? Which those of you in the lab will be doing this week, probably next week. Okay? If we run chemical reactions that happen at very fast speeds and selective for certain functional groups, if there's a visible result, I can say, oh, that substance that I started with had this functional group in it. I can use it as a classification for functional groups, much like I did for IR. Right? You might say, well, but don't I have an IR to tell me that information? An IR is $20,000. The chemicals with the entire waste plan to dispose of it might be $5 grand. Might, and that's a stretch. 20 grand, 5 grand. The classification test makes a lot more sense. Okay? And if you consider speed within it, even to run the IR, you're still taking time. Okay? The classification test happens within seconds in a test tube. Okay? The IR takes 30 seconds, even though they said it was only 10. But that's not your problem. Okay? So, the name for this as a classification test typically gets labeled as the haloform test, okay? Because you form a haloform. Carbon with, or a methyl carbon, so a single carbon with 3 halogens gets the name haloform. So if it was chlorine, it gets called chloroform. Okay? If it's bromine, it gets called bromoform, iodine, iodoform. Okay? The iodoform is the most famous of them. Well, not the most famous. The most useful classification test, chloroform is the most famous. It was like, oh, everybody passes out. Yeah. Okay?
So the other two did the same thing that chloroform did?
No. So what happens is we move from chloroform to bromoform to iodoform. There's an electronegativity difference, yes? There's size, okay? And in size, not just atomic size of the atom, but also mass. Mass size also changes. It's more dramatic. Chlorine is 35, iodine is 126. Okay? There's a pretty big mass difference there. Okay? It is that mass difference that actually makes the iodoform the most famous of these, as far as a classification test. It is so massive that what happens? It precipitates. Okay? Not only does it precipitate, ooh, actually, I lie. I can't remember that. It might be a yellow precipitate. Okay? But I could be remembering that wrong. I think we'll see in a second. But you'll see a precipitate for the iodoform. Would I expect iodoform to do the same thing as chloroform? Well, what is chloroform doing? The whole knockout aspect. Why is it knocking you out? It's smelling. How many of you have smelled a table and been like, oh yeah, I love me some smell of tables? Or the desk, or your pen. It has to do with the volatility. Solids typically don't have a gas phase. They stay. Liquids have some volatility, so you can smell a liquid or some liquids. Gases are already in their gaseous state. It's very easy to smell them because those particles make it into your nose very quickly. So chloroform, being less massive and less dense, has a relatively low volatility or relatively high volatility, which means it turns into the gas very quickly. So it can suffocate you. And that's why I think that's why you pass out. Okay? It's the lack of oxygen. Iodoform, being massive and precipitates, is it going to have much of a gas state? No. So is iodoform going to do the same thing as chloroform will? No. Okay. Same deal for the bromoform. All right, let's see. Ha! What did I say? Color? Did I say the color? Yeah, look at that. Isn't that awesome? Okay. Yes, this is a silly question. I'm not a fan of this, but they do ask it in this way. Which compound would give the yellow solid HCl3 when mixed with iodine and sodium hydroxide? What the hell? Yellow solid? Okay. This question gets at two pieces of information. Okay. The first piece is, did you do it in lab as a classification test? If you did it in lab, you'll remember the yellow solid. Okay. If you didn't do it in lab, it would be nice if you had some kind of hint to help you through it. Mixed with iodine and sodium hydroxide. Sodium hydroxide and your halogen. Okay. So take advantage of your questions. Sometimes they'll give you stuff that's like, did you memorize this one random fact? Cool, here you go. You now have the answer faster. Other times they'll give you a little bit of background information that you can still derive it and get there. Okay. Sometimes. Right? For sure, there's a question that I find super irritating on your test that I won't tell you about, but you can talk to me about it after you take the test. That's just like rote memorization, and it's just like, why is this even on the exam? Okay. I'm aware of it. I factor that in when I calculate grades. Okay. But it's super irritating. I want to like call them up and yell at them because I think it's stupid. Okay. So our haloform reaction, your textbook goes through a pretty nice mechanism for it. So there it is. Okay. Which would then move us into the next section, our hydride nucleophiles. Okay, we saw hydride nucleophiles before. They came from sodium borohydride and lithium aluminum hydride. Okay, and when we talked about those two reagents, they had different functionalities. The different functionality was due to what? Boron versus aluminum. Okay, different elements, same column, so they have the same general reactivity. What is that boron versus aluminum difference? Size. Aluminum is larger, which means the aluminum, the metal hydride bond is longer, meaning the hydride is now more accessible, making it more reactive. So that size contribution makes the hydride on lithium aluminum hydride much more reactive. What else is different between boron and aluminum? Mass is size. The electronegativity. Boron is more electronegative, meaning what is it doing to the hydrogen? Holds it tighter, which makes the sodium borohydride less electronegative or lithium aluminum hydride more reactive. Right? They both go hand in hand. Right? What's the other big difference between them? Sodium borohydride, lithium aluminum hydride.
Sodium versus lithium.
Sodium versus lithium. Right? Sodium is larger, right? And because of that is more polarizable, right? And generates or has weaker interactions with negatively charged species. Okay? Negatively charged species like the oxygen after the nucleophilic attack. Lithium, being smaller, has a very tight coordination to the negative oxygen, which helps polarize and make that carbonyl more reactive. It's a weird nuance. I'll draw it up in a second. Don't stress a whole lot about it. You at least get the difference between them. Yeah? Okay. So, sodium borohydride with a ketone. We add hydride. Yippee. How does that change when we move to an acid chloride? Do we still have a polar pi bond? Yes. So what should we do? Attack it. Attack it with what? Fire. No. So there's our hydride. Right? Now what happens? The electrons can come back down. We can kick out the leaving group. And what do we have? How many carbons? 3, right? Yeah. We'd have an aldehyde. Does sodium borohydride react with aldehydes? Yep. What happens? It does it again, and we would end with not no oxygen. Okay? The no oxygen, the complete removal of our carbonyl, went back to, they had names. There's the Wolff-Kitchener, I remember for sure. That's the hydrazine. Clemenson, which is that the zinc mercury? Clemenson is your zinc mercury and acid. And the last one, the dithionyl, the dithiol, and rainy nickel was, or is it just rainy nickel? Okay. So you got to remember those. That's to completely remove a carbonyl, and that's specifically looking at our aldehydes and ketones. It's going to have a real hard time with an acid chloride. Why would those have a hard time with the acid chloride? The acid chloride is so reactive that in all of those cases we have some level of nucleophile, even weak nucleophiles, which would convert it probably to the carboxylic acid. Then we'd have to go through and do the reaction or reduction, and they're going to have a hard time with the carboxylic acid. Okay? So we end up dropping down to the alcohol. So if we have these acid chlorides, or really any of our superactive acid derivatives, they will get reduced twice because that leaving group can get kicked out. Okay, that's the important distinction to remember. So we form our aldehyde, then to our alcohol. Okay. But we had two. That was our lithium aluminum hydride. Our reagent difference we addressed with our boron versus our aluminum. Come on, pen. The boron with versus the aluminum. Do I need to try and attempt to draw those out? Or do you guys think you got those? Yeah, we got them? Okay. So let's take a look at what I was talking about with the sodium versus the lithium. Okay. This is kind of a weird one that really plays a larger role in inorganic chemistry. This is where they start to talk about this in a little bit more depth. Okay. Our hydride comes in, attacks, and we get set up with our negative oxygen, right? Okay, so there's two ways that we can facilitate that reaction. Stronger nucleophile, hydride's pretty much as strong as that nucleophile can be. Okay. Both sodium borohydride and lithium aluminum hydride are going to supply that hydride. Okay. There are key differences between the sodium and the lithium. Okay. It is easiest to see that difference from the negative structure, and even then it's not the easiest to see. Okay. What we're talking about is that that negative oxygen is going to interact with the positive sodium or the positive lithium. And what we're talking about is that attractive force. Okay. Sodium being larger, what is that attractive force, or the distance? It's a longer bond, which means what is happening to the negative oxygen? It is less neutralized, which makes it less stable. Okay? The lithium, being a smaller atom, is now much closer to the oxygen, meaning it can neutralize that negative oxygen a little bit better than the lithium. Why is that important for this reaction? Okay, well, if we looked at kind of an energy diagram to vaguely address this, let's start with sodium. Right, it's an exothermic reaction. It's a lot more exothermic than that, but let's just say it was. That's close enough. The lithium reaction is going to do virtually the same thing, except be slightly more exothermic. Okay? Because it can stabilize that negative oxygen a little bit better. What does that mean? Which of those reactions is going to be more favorable? The lithium one's going to go a little bit faster. Our lithium aluminum hydride is the stronger hydride source than our sodium borohydride. The lithium and the sodium aren't changing the hydride, they're changing the oxygen. Okay? That oxygen interaction can also happen at the starting material. The lithium one polarizes the oxygen better than the sodium because, again, shorter bond. Okay? I personally think it's easier to see with the charges, but it's officially going back to our starting material. So it's really affecting what's happening out here. Okay? Kind of makes sense? Okay. Why does that become important for us too? Well, then we have our list of all of our carbonyl compounds. Not all of our carbonyl compounds, primarily the ones that we had before. Sodium borohydride and lithium aluminum hydride are going to react slightly differently on this scale depending on the activity. Okay? So the acid chloride, we should all be in agreement, was super, super active. Okay? What was another new functional group on our list that's not drawn up there? So don't try and cheat and look at that because you can't. Could look at the carboxylic acid. Dang it. So I'm just going to shift over here. What other functional group? Do not say carboxylate. Carboxylic acid, our amide.
Ester.
We have the ester. Now, the one I was fishing for is, of course, the last one. It's also probably the hardest. The anhydride. Okay. Where would we insert those into our old system? Okay. The acid chloride for sure is the most active, okay, because it has that green leaving group. Okay. How about the anhydride? Should I be placing it here, here, here? 1, 2, 3. Feel free to stop me anytime, or I can draw them all out.
Right after the chloride, acid chloride.
So you're saying right at 1, and you just wanted to watch me draw it all out. Why would you put it there?
Because it has resonance.
Wouldn't resonance make it more stable? So less active than the...
But it'll resonate only to one side, making the other side very slow.
So yes, there's resonance one side, making the other side more active than our aldehyde sequences. So we would expect that to be higher in activity. Okay. How about the ester? Right after the anhydride, so you're saying to drop it in there too? So it should be more active than our aldehydes? No, why not? What is that resonance doing to my electrophile? It's stabilizing it. The aldehyde doesn't have that. Does the ketone? No. Our amine is probably even better than that too. We're drifting somewhere down here, and I don't remember which place, but it's one of those. Okay. The ester and the acid are roughly the same. The amide was even lower than all of those. Okay. So recognizing where they all fall relative to each other becomes important because we need to know something about our sodium borohydride and our lithium aluminum hydride. They're going to react with the most active, absolutely. But at some point, what's going to happen? What's not going to react? The sodium borohydride will likely stop reacting, and the lithium aluminum hydride will continue to do so. And yep, that's what happens. If we look at our sodium borohydride, it will react with our acid chlorides and the acid anhydrides. As soon as we hit the ester, they have this note that the reduction is very, very slow. Okay? It is so slow that it is not useful. Don't do it. Okay? They should really have that marked out. Okay? They shouldn't even have that shown on there. as a reaction. And I think they even make note of it in the book, like, this is horrible, you shouldn't do this. Don't show it.
I don't remember if they asked, but
Then you have the carboxylic acid and the amide. If we go through and look at lithium aluminum hydride, what does it do? Everything. The one kind of weird one that you need to watch out for is the amide in the lower right-hand corner. Okay? Because most people notice that when we go through and look at these, what happens? We do the reduction, we end up with what functional group? Alcohol, 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 alcohol. Then we get to the last one. In that lower right-hand corner, it's an amine. Why did I not get the alcohol?
she started with amide.
Okay, started with the amide. That kind of makes sense. Okay, really, what it's going to come down to, we draw all that out or erase all that, is that we'll end up at this situation with our. There's not an R group. That would be 5 carbons. 5. Fine, I'll just draw it again. See if I care. Right? Which one is the better leaving group, oxygen or nitrogen? Why is oxygen a better leaving group? Why? Oxygen being more electronegative is the better leaving group. You might say, well, isn't that an O minus? Fair point, but it can leave into the solution where the lithium aluminum hydride will coordinate to it better. Aluminum will actually interact with the oxygen to form an aluminum oxide, okay, to stabilize it, and we keep the amine. Okay? So what I would argue is don't worry about what that oxygen is doing, except that it is a better leaving group because oxygen can hold the electrons better, okay, than the nitrogen, which means the nitrogen stays behind. And yes, this would be one of those, but don't you have O minus 2, sorta? That's where the aluminum comes in to kind of help out, okay? And you kick out the oxygen, you then have the imine. The imine can get reduced a second time by another lithium aluminum hydride. Kind of makes sense? It's a little bit more complicated than that, and by a little bit, I mean, I think actually significantly more. But that's close enough for what we need. Kind of makes sense? Okay. So why barely? Why would it not reduce? See, even look at this. The synthetic step that the textbook shows us. What are they showing happening to the ester? Nothing. Don't show a slide or build a figure that says it happens. Like, that's just rude. Okay. Why is it only reducing the ketone and not the ester?
The ester has resonance stabilization between the oxygens.
The ester has that resonance to stabilize, so we don't get a good electrophilic carbon. Same deal with the amide and the carboxylic acid for that matter. Okay? So yeah, there's all those. We already talked about those. Okay? So why can lithium aluminum hydride do all this? This largely has to do with the lithium contributing in and the aluminum helping to pull some of those oxygens and help those act as decent leaving groups. Okay? So you're getting some kind of weird secondary chemistry happening there, which I vaguely think the textbook goes through and addresses. But again, it's not that big a deal. I just want you to focus. Lithium aluminum hydride will do it. Okay? So what would we expect as a product here? What, you can't name that? I am kind of kidding. I was waiting for that one to come out. If you don't know how to name it, then I can make up whatever name I want. You can't challenge me. So, neener, 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 take that. The lithium aluminum hydride should reduce away that carbonyl that we left with the amine. Okay. Another interesting feature about our lithium aluminum hydride, it is a reducing agent, right? Okay. It reduces pi bonds. Did it reduce all pi bonds? No, what did it only reduce? Polar pi bonds. Okay, so remember the bits and pieces behind those reagent functional groups. Okay, let's say I have an acid chloride, but I want an aldehyde. Could I potentially stop it? Of course. If I ask questions, of course we can. Okay. So we got acid chloride going to an aldehyde, and we have an ester going to an aldehyde. In both cases, actually not in both cases. In the first case, that isn't horrible to expect, right? Why is the first one not so bad? Being like, yeah, we can stop at the aldehyde. Chloride's a good leaving group, yeah. Turn it on its head. Why is the bottom one like, whoa, dude, that can't happen? The ester has resonance stabilization, making this electrophile not so good, scientifically. The product of this reaction would be an aldehyde, and as an electrophile would be pretty good. What does that mean? We start with a structure that's not active, we end with a structure that is more active than we started with. It should be more reactive. That bottom one should continue to go. There's no reason that should stop. Okay? The top one, we could make the argument that's okay because the acid chloride is more active than the aldehyde. So we're just trying to get it to stop at a reasonable stage. Okay? The bottom one is kind of out there as far as the chemistry goes. Okay? What's that? Yes. Both of these reactions actually happen. We have to add special reagents. So when we go back, can I go back? Yeah, when we looked at our reagents, we had the lithium aluminum hydride, sometimes referred to as LAH. Aluminum. Come on, pen. And we had sodium borohydride, right? And we said that the lithium and the sodium changed the chemistry, and we said the aluminum and the boron changed the chemistry. Did anybody ever go like, I wonder what would happen if I did sodium aluminum hydride and lithium borohydride? Anybody think about that while they were looking at these? It was like, why the hell would you ever think of that? It's torturous enough. Okay? Somebody did consider that. And guess what happened? Change the chemistry. Okay. What if, let's just pick the lithium aluminum hydride because that one's a little more active. Let's make that our lithium again. What if I went through and said, you know what, I just want to put some carbons in here. You know, just for giggles. I think it'd be fun. Is that going to change the hydride chemistry? Maybe I should be careful in phrasing that. Is that going to remove a hydride from reactivity in this structure? No. I still have aluminum with 4 bonds. I still have hydrides. But what else have I done now? So it's done a couple things. I've reduced the amount of active hydrides. In lithium aluminum hydride, I had 4. Now I only have 3. Okay. Not only that, what does this group have as a characteristic? It's bulky. What is that going to do? Potentially sterically block and prevent something from reacting. And it turns out that yes, we can make derivations of the lithium aluminum hydride and the sodium borohydride. Okay. Pretty much what you need to remember, you see metal, aluminum or boron, don't tell me they're metal, I know. Okay. And hydrogen. Reduce. Just do it. Okay. Put a hydride on the structure. Worry about the details later if you have to. Okay. So if we take a look at that top one, what happened? I did a reduction. I added the hydride. Okay? There was a bunch of this other weird stuff attached to it. I don't know what's going on with that. Okay? Hope there isn't one that shows the full reduction. Okay? Bottom one. This one's even more frustrating because what they show, and totally the wrong abbreviation for it, DIBA. Everybody usually throws in an L. It's usually diball with an L.
That on SmartWorks too.
It's the same people. Was it Boston? Ooh, I think they are from Boston. Daiba. Gotta get me some Daiba. Sorry. Focus. See the hydrogen? And this is where it's helpful to have the L. You have the aluminum hydride. Okay? You're doing that reduction. Okay? What's happening in the top case? O-T-butyl. What is T-butyl? Bulk. Okay? It is the bulk, and dibol is diisopropyl. Okay? Butyl aluminum, or diisobutyl, I believe, aluminum hydride. Okay? Those isobutyls are again large. It's that bulk that changes and modulates the chemistry. Okay? If you really want to push this, those are with aluminums, or sorry, the metal, the other metal, lithium. Okay? You could also switch them to sodiums, and that modulates the chemistry. Okay? So there's a list of reducing agents that all kind of match the same general characteristics. Using our aluminum hydrides or our borohydrides, they're just modifying the structure to target particular chemistries, okay, or particular carbonyls, or for that matter, imines or nitriles. Okay? So just be aware of that. Focus on the chemistry you know. A metal hydrogen bond makes a hydride. That hydride needs to do some stuff. Okay? And with that, we'll go ahead and stop. This just kind of summarizes some better pictures of it.